Welcome to the video for Lecture 10, Section 3. This video describes how interacting first-order processes in series are combined so that we can determine the final process output and any intermediate values we want. The previous video dealt with non-interacting tanks. We are using liquid level in tanks and flow from tanks to illustrate the process even though the concept and the procedure is applicable to any series of first-order elements. The examples we will work with will have multiple tanks in series, and this video deals with interacting tanks. The equations we will generate will be able to calculate the flow rates from all of the tanks and the fluid depth in all of the tanks. This is the sketch we use to illustrate non-interacting tanks in series. With non-interacting tanks, what happens in tank 2 does not impact the flow from tank 1, so it was non-interacting. The relations between fluid flow rate, tank fluid depth, and flow resistance shown here assumes laminar flow. Turbulent flow can be used too. This is the sketch we will use to illustrate interacting tanks in series. The tanks are interacting because the liquid flow rate from tank 1 into tank 2 depends on the difference in liquid depth between tank 1 and tank 2. Since the upstream flow rate depends on downstream tank conditions, the tanks are said to be interacting. Here is the first-order differential mass balance equation for tank 1 after assuming that A1 and ρ are constant. This expression is the same as for the non-interacting tanks. Here is the first-order differential mass balance equation for tank 2 after assuming that A2 and ρ are constant. The expression is the same as for non-interacting tanks. Here is the equation for the flow between the two tanks Q1 in terms of the two-tank fluid depth Z1 and Z2 and the laminar flow resistance R1. This is a new equation for interacting tanks, and the equation relates Q1 to the fluid depth in both tank 1 and tank 2. Here is the equation for the fluid flow rate out of tank 2 assuming laminar flow. We have used this equation before. The past 4 slides gave us 4 equations with 5 unknowns. One of the unknowns is the input flow rate, so we can write the equations as transfer functions. The details for finding the equation are summarized on page 11-6 of the course packet. This slide shows the transfer functions for the fluid depth in tank 2 over the inlet flow rate Q and the tank 2 outlet flow rate over the inlet flow rate. The transfer function for the fluid depth in tank 1 over the inlet flow rate Q and the flow rate leaving tank 1 over the inlet fluid flow rate Q are listed in the course packet on page 11-6. And you will not need to develop these transfer functions, and you can just use them and reference the course packet. Okay, let's compare the time domain results for 2 non-interacting tanks and 2 interacting tanks. Let's look at the outlet flow rate from tank 2. To make things easier, we will assume that the tau values are all equal. All of the cross-sectional area values are equal, and R1 equals R2. Again, we will use a unit step change for the input function Qt, so Qs equals 1 over S. We end up with a transfer function with repeated roots shown here because the tau, A, and R values are equal. The time domain result is shown at the bottom of this page. More details are given in the course packet. Here is the transfer function for the interacting tank problem with the same assumptions. This is the 4th equation on page 11-6 of the course packet. The equation simplifies because the tau values, area, and R values are equal. The course packet shows taking the inverse using the quadratic equation. You can solve it using MATLAB. And the time domain equation is shown at the bottom of this slide. Here, we show the outlet flow rate from tank 2 for both the non-interacting tank case and the interacting tank case. The horizontal axis is time in seconds, and the vertical axis is fluid flow rate. For the conditions specified for the problems, the flow rate from non-interacting tanks was higher than the flow rate from tank 2 for the interacting tank case. Now we summarize the solution procedure. We need to identify the system elements and determine whether they are interacting, non-interacting, have a constant flow, or are nonlinear. Then you need to find the transfer function for each element. In most cases, you will be able to write the transfer function using the ones that we have developed already. Next, you need to find the overall transfer function. You will need to be given either the time domain input function qt or the Laplace domain input function qs. You will use the overall transfer function and the input function to find the Laplace domain expression for the desired liquid depth or outlet flow rate. Finally, you will need to take the inverse of the Laplace domain expression to find the desired time domain expression. This brings us to the end of this video on interacting tanks in series. The next video goes over examples in section 11 of the course packet. Please write down any questions you might have and bring them up in class.